Okay. So we have two unknowns. We want to calculate V naught over here, right? This is our end goal. That's where we want to get to, right? V naught. That's the problem. Vx naught. That's what we want to get to. How fast it goes off the cliff, right? So that means that we want to find t using one of these other equations. We see that V naught x does not go into one of these, so let's use one of these to calculate t, and then we can transfer it back over, right? So we want to so let's see how we're going to use one of these equations, right? So if we use this first one, right, to calculate t, how many unknowns do we have in this first one? We don't know Vy. I'll write this down. We don't actually need to know Vy, and then the final velocity. We don't need to know it in the end. That's why I didn't include it, but we don't know it. So there's two unknowns here. This does not help us, right? This just adds an unnecessary unknown. You know, we really just need these two unknowns. So let's see if we can get it from another equation. Right here, we know everything in this equation, right? We know the distance it travels, y minus y naught, and we know the initial velocity. So we could use this equation, right? We can use this equation. We would just have to use this third equation, right? If we introduce this one, that means we have three unknowns. So that means that we would need another equation. So if we use these two equations, these three, we can also calculate it. But in the end, we can use these two, the position vectors, the position functions, right? So we'll calculate the time using its position in the y, right? And let's write it out. So I could finish, I'll just finish it down here. So our y equation, when we plug in the numbers, y0, that's 0. Or I'm sorry, let's rewrite this. So we have y0, right? I'm just bringing this y0 over to the other side. This is equal to 50. And then since I'm bringing this to the other side, it's just the rest of the equation now. Now, the initial velocity in the y direction is 0, so we end up with this equation. And then when we solve for t, we get this. (100) divided by g. The square root of 100 divided by g. And this time ends up coming out to be 3.19 seconds. So this is the time it takes to fall. Now we have to plug now this time into here and calculate the distance it travels. So now I'm bringing the x naught over to the other side. So now we have, I rewrite this equation like this. This is 90 meters, which is given to us. And then we have our t. We plug it in. And then we solve for v naught x. And we get around 30. The exact number is 28.2 meters per second. So, and we'll use we'll use this philosophy to do all these projectile motions, where we want one quantity in either the X or Y direction, and then we use the other direction to help with the unknowns, to give us more equations to solve the unknowns in the system. All right. Any questions on this so far? Okay. Let's do yeah, let's do a kicked football. So this is example 3.7. I'm going to leave my equations up here since we'll use it. So a football is kicked at an angle of 37 degrees. So let's draw it. So since we're on level ground on a football field, we kick the ball and we give it the initial velocity. So we give it initial velocity. All right, and it occurs at this angle of 37 degrees. Yes, you can, but you have to be quiet. Sorry, guys. Okay, so I'm gonna hold on, guys. I'll be right back. Okay, so we kick the football, and it has the same motion that we've seen in the past. Right, we kick it, and it travels in this parabolic arc. Right, and the acceleration, A, we'll write it down. G in the J direction, in the Y direction. Let me label the coordinates. Right, and it has initial velocity of 20 meters per second. So its initial velocity is 20 meters per second, right? And now for part A, it wants us to calculate the max height. Okay? So where's the max height? It's up here at the top, right? So this is Y max, we'll call it. And this is what we want to calculate, right? So what matters in this problem? Let's see. So we want the max position. So let's first look at this equation. The position equation, right? So I'm just going to rewrite it like this, right? We want to find where this is the maximum. Y minus y0. What is y0? So let's go through it and let's figure out what quantities we know at this position. So what's y0 equal to? We set our origin over here, so it's 0 initially. What is y naught? Do we know this? Do we? I mean, not why not. The initial speed in the velocity in the y direction. Do we know this? How do we calculate it? 30 meters per second? No, that's not correct. We start out at so its initial velocity is actually partly in the y direction, partly in the x direction, and the magnitude is 20 meters per second, right? So we don't know this initially, right? We're not given it. So we don't know why not. What else do we know? Do we know t?
No.
No, right? Let's see what else. So we don't know t, and we don't know why not, right? So we need to find t, right? So we have 3 unknowns, right? And then we don't know why. Or y max at this position, right? And we'll just use y max here. I'll just write y max. Okay? So we need 2 other equations. So we have this. We can't get t from this, right? And so if you look at this equation, we don't know why not, and we don't know this. So maybe this isn't the best one, right? Because we need, for this equation, we need this, right? We'll actually go into this equation in a minute. So I'll show you it both ways, right? We actually took the long way here. So let's take this equation. Again, we have 2 unknowns, or we have 3 unknowns here, right? Yx, y naught, and t, right? So we need to come up with some formulas, right? We need to figure out these 3 parameters, right? So for y0, can we calculate y0 from our initial conditions? Yes, that's correct, Jeffrey. So we can calculate y naught from our initial conditions. So what formula do we want to use for y naught? So for v, for the v naught in the y direction. So we'll just break it down into its components. So it will be v naught multiplied by sine theta over here, right? Sine of 37. So now we have this one. So this is one equation that we'll use, right? And now we need a third one, right? What do we know about, do we know anything else about this problem? Let's think about it. As we get to the top, what do we know about its end-in position at the top? What's Vx? Whatever's related to the initial conditions, right? Because there's no acceleration. So Vx would stay the same. It would be this, right? What's Vy at this position? 0. So we know Vy. We don't even need this equation to calculate Vy at its final position. We have it, right? And then we'll set this equal to V naught minus T. So we now we have V naught Y0 and G. We could use this equation to solve for T. So let's do that. So I'll go over here and we'll set 0 equal to V naught sine theta, which is 37 degrees, minus GT. So then now I'll solve for T. All right. Now remember, I have to use a positive G over here because I already included this negative sign. All right. So I'll have, so it'll end up as this over G. And then T is now equal to 1.24 seconds. All right. And then because our numbers given to us have two significant figures, that's what we'll use. All right. So we'll drop the 4. And now we have T. So let's go back to our original equation to find this guy. This is what we're looking for. Right, y max, we know y0 is 0, so circle both of them. We know T, we know the initial velocity, we know all this, so that we could solve for the distance. So let's plug it in. So then y max, I'll drop out off the y0 since that's 0, and then we'll have this. Oh, this should have been negative. Oh, the T. Squared, and this comes out to 7.35 meters. Okay. Now, did we do it the easiest way? Actually, no, we did not. This would have been easier, right? Because this has the distance. If we would have known from the beginning that y0 or the final velocity is 0, we could have just used this formula, right? Because this doesn't have time in it and it'll give us the distance. So we could have used this one instead as well. 2G, y0, this is what we want to calculate. And then at max, we'll have this condition. Right? And then we know why not, and then it'll come out to the same thing, and we can solve it that way. So most of these problems, there's multiple ways to solve it. So the next one we'll do is the time of travel of the football before it hits the ground. So if you remember, so T time of flight, we'll call it. Right? So we know the time it reaches to the top, right? And because the symmetry of the problem, if you remember, it's just double this time, right? So time of flight is equal to 2 times the time of the height, at the time it gets to the height, because it ends at the same ground level, right? At the same y is equal to 0. So it's just 2 times that amount in this case. 2 times right? Well, we actually, which we already calculated this over here. So the time is 2.22, right? So we have that. We didn't even need to use this formula because we had it down here. And then that's for part B. And then for part C, how far away is it when it hits the ground? So part C asks you how far, right? So here, x0 is 0, right? And then we'll just use this equation over here, v naught t. We know all these, right? We know x0 is 0. We know the velocity. We calculated it over here. And we know t. It's given right over here. So then we have times 1 point time of flight, right? And this will equal the distance that it travels will equal oh, I'm sorry. This is the time to the top. I got confused over here. So the time of flight is double of that. Let me go back. I apologize for this. So I thought we calculated the full time. So the time of flight is this 2 times T max. This is T max. Let me write it in over here. I got. So then this would be 2.44 seconds, right? So this is the time of flight that we did before. Okay? This is the time. And in the book, they included this little, they included this, so it's in the book, they have this. Okay? Now, C, they wanted the full distance, the full distance that it travels. X is equal to this. We do the same thing that I was talking about before, but now we'll use the time of flight. So X is equal to this, and then we'll have times 2.5, and then x is equal to that. And in part D, it asks us for the velocity vector at its maximum height. And we talked about this already. It would just be the velocity vectors, just the x component at its maximum height. And then for part E, the acceleration vector at its maximum height. So what's the acceleration at this point? Anybody? 0. I think you just typed that, Jediah. Yeah, so, well, that's, I'm sorry, no, you didn't, that was already up there. So the acceleration doesn't change, right? We went over this last class. So even though the velocity is 0 over here, put it in the y direction, its acceleration stays constant, right, throughout this whole problem. So now let me ask you, if we want to kick this ball the furthest, how do we figure out the angle? So let's say we you
45.
know. Yes.
It's 45 degrees, no?
Well, how do we figure that out? Yes, the answer will be 45 degrees. But let's actually derive that to show that that's the case. Right? So let's figure out the angle at which we can kick it for it to travel the furthest, right? Because there's this interplay between how high we kick it and its x velocity, right? There's this interplay between, right? We want to maximize x over here, and there's this interplay between its initial velocity and the time of flight, right? If we add to the initial velocity, we kick it lower, we reduce its time of flight. So this is an optimization problem where we optimize these two parameters, right? And how do we find, how do we optimize a function or get its maximum value using calculus? Does anybody know?
Yeah, wouldn't you take the derivative and find where it's equal to 0 to find the critical point?
So we'll take the derivative and we'll find where it's equal to 0, right? So this we'll call the range, and we'll find when that's equal to 0. We'll take the derivative of the range and we find when that's equal to 0. So let's write out the equations. So x naught, and right now we don't have. So let me redraw this. Theta, I'll just call this theta. We don't know the angle. This is what we're maximizing. So let's write Vx as cosine theta, right? And now we put this as a function of theta. So x is now a function of theta, right? And now we have to put t as a function of theta, right? So the best way to do this is to use, we'll use this equation, right? So we'll use this kinematic equation, right? Because we know we have y0 and then we know g, and the only thing that we don't really know is t here, right? Why? So we know this displacement, right? It travels back down to its starting position, so we know that this is 0, right? We don't want to use this. We don't know the final velocity. We never calculated it in the y direction. Same thing over here. So we'll use this. y0 plus is equal to this, right? This is 0. Now the t's, the exponent over here cancels with this t, and then I just solve for t, right? So then it comes out to be 2 vy naught over g. And here g is 9.8, right? Because we included the minus sign already. So we usually write g as a positive value, and then we include the minus sign. So now we have t as a function of the initial velocity, and we know what the initial velocity is. Let me just erase it over here. I'll erase what I just did. All right, and we know that this is v initial times sine theta over g. So now let's plug this back into t. Let's make that t. And now we'll plug in the full formula. Cosine, I'll just put, let me put, instead of the number, let me just put v naught over here so that you know what it is. And we'll plug in the numbers after. Okay, now we have that. Let's gather the terms and simplify. So it's this times sine theta, right? And then to find x max, this is equal to when theta max over here, right? When we plug in theta max. And then the way we find theta max is when we take the derivative with respect to theta, and it's equal to 0, right? So we got to solve this problem. So let's take this derivative, dx, d theta. These are just, the first parts are just constants. Then we do a derivative by the product rule, right? So what is this? So what is the derivative of cosine? Anybody? That's correct. And what's the derivative? So it's negative cosine theta. And now if we look at it, we'll have this, right, multiplied by sine, and then plus what? We leave the first part alone, and then what's the derivative of sine? Cosine, right? So what we get is, so we get cosine squared minus sine squared, right? And then we set this equal to 0 for max. Set this equal to 0. And what we'll find is that these two have to equal each other, right? Because this is 0 on the other side, these come across. So we get this. 1 is cosine squared equal to sine squared. And this occurs for, and this implies that theta is equal to 45 degrees. Right? So the way to do this is you divide this over here, so you get tan squared theta is equal to 1. And then you do the inverse tan. Inverse of 1 is equal to theta, and then we get 45 degrees. All right, and we find that. And so for neglecting the wind, any wind resistance, you always want to kick it at 45 degrees. So if it's on a beautiful day and you're playing football, you always want to kick it at a 45-degree angle. And then depending on how the wind goes, you want to adjust accordingly. If the wind is against you, you want to kick it lower, right? Because you don't want it to hang in the air to slow it down. And then, or if the wind is with you, you want to kick it higher because it'll pick up more velocity. Okay. Let's see. And then if we draw the trajectories, just real quick, let me draw it. So let's say if this is 45 degrees, so for most of these distances, for all these distances, except for the max, you'll have two solutions, right? To that range problem I had up on the board a minute ago. So if I kicked it at 60 degrees, it'll go a little bit higher and it'll land over here, right? Now, if I kicked it a little bit lower, let's say at 30 degrees, it would go that same distance, but with a different trajectory. And this is 30 degrees. We start at 30 degrees. I wrote it up here because I ran out of space, but this is the angle that the velocity vector makes, these two. And we see that they'll land at the same spot, right? Because you'll get two solutions to this problem. So. And then we could use the range. And let me write a final solution to the range. So the range, if you remember, we had 2 V naught over G, right? It was cosine squared minus sine squared. By a trig identity, we can convert the two cosine squared theta minus sine squared theta into a simple into a single sine function. So this will come out to be this sine theta.